our first up at bat. So if you want to go ahead, you should have co-host capabilities. Everybody make sure you're on mute. DeAnn, I'll let you introduce yourself and kick it off. Hey, Jimmy.
All right, so let me go ahead and first get this in, all right, presentation mode. Can you see my screen yet?
I cannot.
Okay, let me fix that. Speaker view, okay, that's not what I want. Usually, oh, here's share screen. I hit the wrong thing. There we go, screen 2, there we go, and share. And how about now? Look good?
We're beautiful.
Okay, excellent. So my name is DeAnn Presley, and I am a soil scientist at Kansas State University. I started in 2007, and I've been working on soil health, cover crops, tillage, and I do a lot of different things, honestly, but those are some of the main things I've been working on. And I was asked to talk about soil health testing today, so I'm going to keep it a little general, but I will say that I'll get to that in a second, what I was about to say. So, this slide, I've recently done a project called the Dynamic Soil Properties Project, and there's a lot of different people. I think there's over 20 states participating now, and in fact, Paul in Texas has one of the sites as well. And so when I think about soil health testing and what makes a soil good, if that's what you're trying to understand, are you trying to see if you're making soils better with management? So these pictures are all about within a mile radius of each other. They're all the exact same soil type, same soil forming factors, and their exposure on these is a little different. One of these was in the afternoon versus in the morning. I could probably mess with the lighting on that, but really, just thinking about what are the properties you can measure? How do you decide if a soil is better or worse? So that's what we're going to talk about now. So when I think about soil health, I think about it as the capacity of a soil to function. Does it do what you want it to do, or could it be better? And biological properties. And then I often think about organic matter. Is organic matter a physical, a chemical, or a biological property? And really, yes, it's all of those things. So if you think about soil health as like a three-legged stool of physical, chemical, and biological properties, I almost think about organic matter as being the seat, because it's connected to all of those things. And I'll explain that as we go on. And how long does it take a soil to change? I get that question a lot. If you change a management practice, how long does it take for a soil to change? Get better or get worse? These are good questions. And then what are soil functions? People talk about, does a soil function? So I think about nutrient cycling. So again, that's Brian's area of expertise, right? But nitrogen, phosphorus, carbon, and sulfur, these all go through cycles where they change, go through the organic and the inorganic, associated phases. Water relations. This is one I think about a lot. Does water go into the soil and infiltrate, or does it run off? We know that runoff is a problem, generally speaking. It takes sediment, takes nutrients, takes pesticides away with it. So infiltration, especially in a water limited region, right? Precipitation, capture, and storage is what it's all about. Diversity and habitat for microorganisms. I'm not going to steal any thunder from Gail because I'm sure she's going to talk to us about soil biology. And then soils filter and buffer. So water, we need water to get in, recharge a water table. But as it does so, it detoxifies, degrades, immobilizes different substances that might be in water. Think about, wastewater from a septic system. And I'm a pedologist by training. So if any of you knew Brian Carter when he was there at Oklahoma State, he was a pedologist. So where do soils come from? And so I threw up a map of mollisols here. So there are 12 soil orders, and mollisols are the really good ones. If you've got a lot of mollisols mapped in your state, that's a good thing because they're the ones, mollisols are by definition high in organic matter. So they've got a nice thick organic matter rich topsoil. So these are just, if you think about where soils come from, we're talking about the 5 soil forming factors. So we've got parent material, or so climate. So climate affects things, right? So the hotter or the colder a climate is versus the warmer a climate is, that'll affect the properties that the soil has. And organisms, 1 second. So organisms would be like prairie soils, or are they, 1 second, I got somebody making some noise here. No. There we go. Organisms. So are your soils formed under prairie? Are they formed under forest? Those are sort of the big splits there. But then also organisms are a big thing that people think about in soil biology and soil health right now. So more organisms, are more organisms better? Or what kinds of organisms do we want in our soil profile? There are some that are better and some that are worse. Then there's the whole pathogen prey network too, right? Summit, back slope, foot slope. Those are all properties. Parent material. This is one of my favorite things to think about. So glacial till versus lust-derived soils versus alluvium, they're all going to have different properties. And then time. Time is a very important soil forming factor. Soil formation itself is very slow. People have calculated different rates of formation and they happen at different rates in different places, but soil formation is a very slow property. And so I think about this with respect to soil health too, because time is an important factor. And then humans. So what's the difference between these two photos? If you look at the one on the right, the one on the left, thinner topsoil, yellower looking subsoil, a little higher in the profile. And these were taken under the same lighting conditions. So the difference between these two photos is about 150 years. So we've got cropland and then just over the fence in a pasture that was never farmed. So this is a pretty consistent number that cropland is usually 40 to 60% eroded compared to an adjacent pasture. So if you can compare a native soil or a near native, so pastures are not, native prairies exactly, but if you think about if they've never been tilled, they're a good approximation, as good as you might get in an area. So usually they're about 40 to 60 croplands are 40 to 60% eroded compared to, nearby pastures or native. So humans, the point is the humans are the sixth soil farming factor. We change things rapidly. We can change things, in a second with a bulldozer or with heavy equipment doing, installing light poles or something, right? So if you think about this, we could remove topsoil immediately. In fact, I had somebody ask me a question about, can I remove my topsoil and sell it and then still farm that land? And I said, probably not. That's probably not going to work. So to improve this, or can we ever go from left to, we can work that way, and it starts top down. Changes are going to be small. We can work that way. I don't know that we'll ever replace, half this thickness again, but we can sure improve that surface, and improving the surface has a lot of benefits that I'm going to show you. So let's talk about testing and when should you test. So soil health testing packages at commercial or university labs aren't cheap. Generally speaking, most soil health packages start around $50, and you could end up closer to $100 depending on how many different tests you add on to that. So, and what are you going to do with the data once you get it? So one thing I think about is, have you ever seen those like 23andMe or Ancestry.com and all the different companies where you can spit in a tube and get your, you can know something about your heritage, learn something about your heritage? I haven't done it yet because I'm too cheap to spend the, $99 or $199. But somebody in my family has done it because they are actually hoping to reconnect with somebody that was adopted in their family. But there's other reasons to do genetic testing, right? I'm thinking for human health. So if you're looking for the breast cancer gene or other genes for other known issues. So my point is that if you have a reason for doing testing, then it's worth it. But if you're just doing it for interest, you got to decide, is it really worth that expense? So here's a suggestion I have. And this is that if you sample fields when a big change is happening, maybe you just acquired the field, it's a new field you purchased or a new field you're picking up for renting, or you're changing X, Y, or Z practice, like you have bought a new implement, or you're going to switch to no-till, or you want to start using cover crops, or you're going to start adding cattle, a big change, that's a good time to do that testing. Just like human testing, if you're really out of shape and you need to get a physical before you start working out or something, it's a good baseline measurement to do. Or if you're looking to add something expensive, like an amendment, or a biological that you want to try out or something, I think that's a really good time is to do some baseline testing before you start something new. And then, like I said, you can get commercial lab packages at many private labs now. It's a lot of different labs are doing this, so just check around. I don't want to endorse any one particular private lab versus another because I think they're all good and they do proficiency testing. But as far as university labs go, one that's doing a bang up job is the Missouri Soil Health Assessment Center at Columbia, Missouri. So I send samples there myself. Sometimes I have too many, but also they have a particular test I like that I can't run myself. And so they do a nice job. And so I give them 3 pluses. The Cornell Soil Health Lab in Cornell or in Ithaca, New York is really nice. They do a lot of really cool things, but I don't know that their fertility recommendations would work. I mean, for us in the Great Plains. So, that is part of their test. They give you back physical and biological things too, and then they give you the nutrient testing. And so maybe the nutrient testing wouldn't have as much applicability for you. So it might be, kind of a waste of money. And then I don't currently know what's available at Oklahoma State or your local university from wherever you're watching this. But just ask, I would say Brian would be a great person to start with at Oklahoma State to ask what's available. What can I get? And then another way to get some good data is through working with researchers on on-farm experiments. So that's I do almost all of my research on on-farm experiments with producers because I like to work at field scale, big plots, big equipment sizes. And so that's a great way to get that info is because then I'm going to share that with my farmers. And usually that's why they cooperate is because they're interested in the study to begin with. And so I'm going to give you some DIY ideas too, because I kind of like to DIY things. Or at least I like to try them out to see what I think about them. So I'm going to give you an idea at the end. So even though I showed you that eroded soil photo, I wanted to say that the good news is that research shows that we can improve soil health, and we do. There are known ways we can make some changes. And information's in demand. People want to know, is soil health, is it profitable? Is it productive? How does it affect soil-water relationships? I think Paul's going to talk about that. Or weeds, Josh is going to talk about that. And then a lot of people ask that question about how fast will my soil change? And sometimes I say, well, the real answer is how bad was it to start with? The worse the soil is, usually we can get some quicker return. Soil, it's adding on more things. It's almost a little bit slower to change because if it's really degraded, doing anything that improves aggregate stability, which is like my favorite soil property, is a good thing. And you'll get a pretty large increase right away. Law of diminishing returns, right? So I'm going to talk about soil physical properties now, and I'm going to talk about things we can measure and reversing the effects of degradation. So aggregate stability. So sometimes we talk about this. So I'm going to give you a graph, but then I'm going to show you some pictures. So with aggregate stability, one of the things we look for is mean weight diameter. So this is like your grade point average at school, right? So average out your A's, your B's, your C's. What do you get? You get your average to grade point average. So this is in millimeters. So, and this says Wichita Spring 15. And I'm going to show you that in this case, purple is bad. So tillage, we have the smallest mean weight diameter. And then these other treatments involved cover crops, whether that was alone or in combinations of things. So these red ones were fall planted cover crops versus green ones were spring planted cover crops. And so the summary point here is that whether we planted a fall planted cover crop or whether it was a mixture or single, it didn't matter. They were all better as far as their aggregate stability than the one where tillage was done both in fall and spring. So this one was a small plot study. And this was a soil health project involving pumpkins. But the point is that we saw a huge difference. So this was a soil that was pretty beat up. This is Wichita, and this was a sandy soil. So a dramatic change happened. So the difference between 2 and almost 5, that's a big difference for the mean weight diameter of these aggregates. So I'll just show you a quick little illustration. So and you can do this yourself, and you've probably seen NRCS do this 100 times by now, but just take water. So this says, and then you take similar size little peds of soil. So then drop those peds in water. So conventionally, you can see from the side, it's starting to slake. No-till looks like it's holding together, and there's a little air bubble. And this one's a native prairie, and this is from above. So you can really see the difference now, how it's starting to slake. So when we talk about aggregate stability, that's all it really is we're doing this only with a machine. So with a machine and different sizes of sieves, and they go up and down for a known amount of time. It's just a way to quantify what I'm showing you here. So I want to talk about organic matter. Organic matter is key. You all know that, right? And the thing about organic matter is if you measure it now and you go back and measure it in 3 years, are you going to see much difference? Probably not. It's a slow moving number. Just like if I started working out now and measure my cholesterol in 3 days, it's not going to be a lot different. But if I do a practice consistently for a long time, I start to get some pretty significant results over time. So this is, so I want to show you this one from a study where both soils received the same N rate for 30 years, and one was tilled and one wasn't. So this is organic matter. And this was both at 135 pounds of nitrogen. And so 2%, like 2.2% is the organic matter for this one with the conventional tillage versus probably 3.1% for the no-till. And this was showing, this is showing you that this is 7.5 centimeters, so 3 inches. So the upper 3 inches was where that difference occurred. But you see how they get closer together between 3 and 6 inches. So like I said, with soil formation happening from the top down, that surface is important. So even if you're thinking, oh, it's just the only top 3 inches, well, that's the gatekeeper, right? If your top 3 inches of a soil can improve, water can get in and then it can soak in slow. But if it's sealed off, if that top surface, even just the top few millimeters gets messed up, whether that's through the aggregates falling apart after some raindrop impacts and seals, that's it. That's game over. You've all seen a sealed off soil where then water runs off, or it's crusted over and seedlings can't get through. So 3 inches is a big deal here. And these are large differences. And this is bulk density. So bulk density is a measurement that if you think about like the carbon trading markets that people have talked about, have tried over time and have, they kind of come and go, but I think they're coming back again. Bulk density is a measurement that you always have to take along with the organic matter, because if you have different densities of things, so organic matter, we report that in a concentration, right? A percentage. To really know if we're storing more in a soil, we need to know the bulk density so that we can multiply that. So then you multiply the organic matter times the bulk density times the depth of the soil that you sampled, and now you can get to tons per acre. And that's how it's measured and traded and stuff. So if you really want to know if you're making a difference in your own soil too, bulk density is a good thing to measure. And so as with most things, with density, density, you don't want something too light and too fluffy, right? Usually you'll see that after tillage or coming out of the winter, you see something a very fluffy, friable surface where it's frozen and thawed a bunch. So too fluffy is bad, but too dense is bad. Dense is probably worse because plant roots can't get in. If plant roots can't get in, game over, right? Because plant roots is where they're getting the nutrients and water out of the soil. So with the bulk density, then this is the same exact thing, but the no-till was, 1.25 versus conventional till 1.35. So that's a difference. And then below that, no difference. In fact, you can see this sort of start to switch here. So bulk density, this is sort of just a textbook table you can find, but with bulk density, soils with more organic matter are going to have better aggregation. So they're going to have lower bulk densities. And also you can see that it depends on your sand content. So I was just calculating some of these yesterday in my lab. And so I have a study that's in a floodplain, and the bulk density at about 2 feet was anywhere from 1.6 to over 2. And I'm like, is my data bad? No, it's not. It's just because at that depth, I had all different levels of sand. Over there on one side of the field, it was silty, and on the other side of the field, it was, like pure sand. So sands actually have a high density. So if you ever carried a bucket of sand around, you know that. But also, so you think sands are porous. Well, they're full of big pores, but they don't have a lot of the little pores. So that's why, of course, they drain really fast. But anyway, so once you have a bulk density number, then you need to compare it to a table and know something about your texture in order to really interpret that. So the way you do bulk density is you excavate a known volume of soil and determine the dry mass. So whether that's by taking a truck mounted probe and sticking it in the ground and slicing it up. So if you know the height, and you can look up the equation for the volume. So you need to have the oven dry mass of soil and divide it by the volume of soil, and that'll give you the density of your soil. So this is a really, like I said, easy measurement. Well, I always say it's like the hardest easy thing. It's easy in theory, but getting good data, because you try to cut a core up and sometimes they just shatter and go all over the place. So you gotta be careful when you do it. Another thing is making sure that you don't compact it. If you compact that soil through the very action of trying to collect it and take the density, that can be. So that's why I say it's a hard, easy thing. It's a hard thing to do well, but just go slow and you can get it done. Infiltration, the movement of water into soil. This is the exact same slide. This is the exact same site, Wichita, July 2015, as I showed you before. And in this case, again, purple is bad. I got to change that. I should say, orange is bad or something, right? So minutes to infiltrate 1 inch of ponded water, 25 minutes to infiltrate 1 inch of ponded water. That's not good. Versus any of these that have the cover crop, in this case, rye or any of these combos, it was, let's see, one of them was 15, but the rest were all close to 10 or under. So that was that's a large difference. Now, it's not quite statistically significant. We'd like to see that p-value closer to 0.05, but for 3 years into a study, that's how long it was, for 3 years into a study of keeping the, tillage in there, and this soil was tilled heavily its whole life, or, at least for the past 150 years, adding in cover crops. And we actually, in this case, this wasn't full no-till, but they reduced the tillage down to just one pass in the fall. We made huge gains in both the aggregate stability, which I showed you a couple slides ago, and the infiltration. So when people say aggregate stability, what's that matter? It matters for this. It matters for infiltration. Water in, precipitation capture and storage in a dry climate, super important. So last thing I want to talk about, and I know that I'm talking to people from Oklahoma, and that sun hemp is like a thing that sun hemp there's some problems with killing sun hemp. I do know that. So it doesn't have to be sun hemp. You could change sun hemp for cowpeas, and I think you'll get the same result. You'll see in a minute here. But this is a study, again, where we had, this is a wheat sorghum rotation done for 15 years. And I wasn't around. I was in high school when this one was started, but I sampled it at the end of its life in 2009 when the project ended. And so after 15 years, in the 0 to 3 inch depth, again, the soil organic carbon was quite different between the two. So the 3 treatments, there was a no cover crop, a late maturing soybean as a cover crop, and sun hemp. So in those 3, these organic carbon levels are different. And just for a rough back of the envelope, if you take carbon times 2, if you multiply these times 2, that's okay approximation for what the percent organic matter is. So if we say this one is the no cover crop was about 2.8% organic matter, and this one was about 3.4, and this one was about 3.6% organic matter, roughly, they were different. So the 2 that had a cover crop were different than the no cover crop. All no-till, no tillage here. This is all no-till. And then in the 7.5 to 15 centimeter, which is the 3 to 6 inch depth, no difference in those organic matters. Not surprised. Well, a lot of times we see this in the Great Plains. We'll see the biggest gains again in the surface, maybe no difference below that, That just takes time. And again, this was 15 years. And this was with a cover crop every other year for 15 years. And there was also a nitrogen rate in here. So as the nitrogen rate went up, the organic carbon went up along with that. So, and more organic carbon, we had faster ponded infiltration. So 6 inches in 3 hours for the sun hemp, and a little over 4 inches in 3 hours for the late maturing soybean, versus a little over 2 inches. And I didn't say this, but the soil is heavy. This is a Ladysmith soil, so surface is eroded. So it's like a heavy silty clay loam at the surface, and then probably after 6 inches, you get into a silty clay. So this is a heavy, sticky soil. So these are really amazing infiltration rates for a heavy textured soil like that. So the last thing I'll talk about is worms. So these are weird units. This is because we converted it for something, but this is in a cubic yard of soil. So imagine a cubic yard, 3 by 3 by 3. If you were going to go dig up 1 cubic yard of soil, so under 100 worms in our no cover crop versus 300 worms in our late maturing soybean versus almost 500 where the sun hemp was. So maybe it was the worms, but were the worms there because, the worms were there because of the cover crop, right? So the worms and the cover crop, it's everything together. So I think about it this way. This is a sun bear at a zoo, and it's licking the window because there was honey put on the window. So when I saw this happening this one day, I just had this thought of like, sometimes people ask, well, should we add microbes to our soil system? I think, well, if you give them the right habitat, they will come. So I said, do I feed the bears or do I just make them the habitat, the bears being the soil microbes? So with that, I think I'm probably getting short on time. So Brian, my other favorite Oklahoma Stater. Should I wrap it up?
That's perfect, because that would lead in, and it's going to be a gap now. I kind of wish I'd reorganized it, but that's a beautiful lead in to what Gail's going to be talking about later. So that's perfect. Any questions for DeAnn before we move to Paul? I'm watching chat, so if anybody wants to type in on the chat. or text me for those of you guys have. Okay, I've got a text message coming in, yeah. So as
okay,
I want to read this, and I haven't pre-read it, so we'll just roll with it.
Okay.
You mentioned as N rate increases, soil organic carbon increases. Brings up a question to me that as we get more efficient with nitrogen in wheat, can we unknowingly decrease organic matter with time?
Ooh, that is a great question, and I honestly haven't entirely thought about that. Man, I kind of almost want to say, I feel like Gail would be better at answering this question. I know she works in, native ecosystems more than managed ecosystems, I think, anyway. But that is a really good question.
We actually have data that could answer that to a degree.
Okay.
Gail, do you want to jump in, or why don't we leave this for the round table and we kind of all bang it around in the round table? Is that okay?
That'd be good. We'll just push it off. I like that.
Okay, that's
yeah,
what I'm good.
And I'll think about it. I want to think about that because that is a good question. I think about that with respect to sometimes with irrigation.
Yeah.
What I mean by that is this. So with irrigation, when you add more irrigation water, you have a chance of leaching salts through the soil profile. So if you have less irrigation, or we're trying to get more efficient with irrigation, are we leaching salts out of the profile less? It could, so could we unknowingly have this unintended consequence? I haven't thought about it with respect to the exact question answered, but it's a good one.
That's the nice thing of having long-term studies that are 50 to 60 years old and both been conventional and no-till for 15 years. And so we've actually got a pretty good data set that talks about that. I wish I'd thought about this and I could have had the slides ready, but we'll move on. So
Brian, restate that question for me, would you?
So Gail, the question was, as you're thinking about it, if nitrogen rate increase as nitrogen rate increase, soil organic matter or soil organic carbon increase, that increase over time. So the question was, if we're becoming more efficient, because we could be honest and say that most of our nitrogen is fairly inefficient. We're over fertilizing, which leads to the ability to build more organic matter because of the C/N ratio, all that good stuff. But if we become more efficient, if we get to be much more optimum and efficient on our nitrogen, are we likely to draw down or limit the build of organic matter?
But if most of that nitrogen that we add is actually lost, it like lost to the aquatic systems, I don't know that it would less, but we lose less.
Yeah.
I don't know if the system is actually going to be compromised by that.
We've got some stuff, and I'll talk about it later. We've got some stuff that would answer that to a degree. So, all right, I want to stop this. I want